Hi, I'm Matt Tolladay, and I'm going to talk to you about Piezoelectric Atomistic Finite Element Modeling, which is the most ridiculous name I could come up with. Hopefully I can explain it a bit to you by talking about the challenge that we were trying to deal with. We're interested in trying to model the piezoelectric properties of molecules made of a large number of atoms, on the order of hundreds of thousands. And do it rapidly, so you could use it for, say, designing nanoelectrical mechanical devices. The traditional way in engineering is to use finite element modeling, which is great for macroscale stuff, as long as it converges. But one issue you do have is once you get down to the molecular scale, you end up with this very much discrete particle system, of which we normally use something more like molecular mechanics or even density functional theory to examine. However, these are prohibitively expensive computationally. You couldn't really rapidly iterate on a design using that. So instead, we use a mixed method, whereby we take a frame structure and model it in FE, with the atoms becoming the nodes of the structure and the molecular bonds becoming beams. For the beam properties, we have to borrow some constants from molecular mechanics. And once we take this, we have a deformable standard FE sort of structure that we can deform, work out where the atom's going to be, calculate some charges for these atoms, which is also slightly more complicated than it sounds. And then from that, we can do some various bits of physics, which I did for a boron nitride nanotube to generate piezoelectric tensor coefficients. We found we could get a reasonably good response, reasonably good result from that compared to higher fidelity modeling such as DFT. The difference was we could do it for 100,000 atoms instead of a dozen. And that's it really. Thanks for listening.